This is Measures of Variation, Part 3. This focuses on the range, but we also do a little bit of review of some measures of center and other measures of variation in context. So the range of a set of data is the difference between the maximum and the minimum data value. So the range is just simply the largest data value minus the smallest data value. So if we take our example of 6 randomly selected beagles visiting the vet and their weights in pounds, then we just look at the data. What's the largest data value? What's the smallest data value? We subtract the two, and our range is 11. So it's a very simple measure of variation. It's easy to calculate, and it gives you some information, but could also be considered a little limited. One place where it might be useful, if I give an exam and I tell you that the range is 84% out of 100%, you'd say, wow, there's a lot of variation in those exams. Some people did really well and some people did really badly. Whereas if I tell you that the range was 8%, you'd say, oh, everybody was pretty close together. But that's not telling you, are they close together and they all did very poorly, or are they close together and they all did very well, etc. So there's a lot of information missing from the range. And like many of these measures, it can be useful in context with other measurements as well. So with that in mind, let's look at an example together. Let's look at the tale of 3 exams. So say we have a class with 12 students in it, and they take 3 exams throughout the semester. Each of these examples has the same range. And what I'd like you to do is take a quick look at this data for exam 1, exam 2, and exam 3. And I'd like you to see, for which data set do you expect the largest mean, and for which data set do you expect the smallest mean? You can do these without actually calculating. You can also calculate if you would like for practice, but part of what I'd like you to do here is just get an intuitive sense of, looking at a set of data and getting a feeling for the mean, getting a feeling for the standard deviation, and getting a feeling for skew. So again, which data set do you expect to have the largest mean, the smallest mean? For which data set do you expect the largest and smallest standard deviation? And for which data set do you believe that the difference between the mean and the median will be the largest? So pause, take a look at those, and we'll talk about it in just a moment. Okay, so let's take a look at these 3 exams. In exam 1, we see that there's this sort of major outlier on the low end, where one student got a 12% or a 12 out of 100, and everybody else had an A or an A minus. And so these are all kind of clustered together. Let's look at exam 2 and sort of see what we observe there. Here we see that 12, again, is a bit of an outlier. And 96 as well is an outlier too. So it looks like one person did really poorly, one person did really well, and everybody else had a score that was pretty close to 60%. So hopefully the instructor in this case would be curving that exam or thinking about how to inspire the class to do better or something. Again, these are fairly clustered together. Clustered together. And in our last example, we've got this big range. Well, the range is, again, the same. I should say that the range in each of these cases is the same. The range in all 3 of these exams is 96 minus 12 equals 84. So the range is the same for each of these cases. How about in exam 3? The difference between these exams is pretty consistent. So this is sort of more evenly spread out. there's maybe 8 or 9 or so points, 7, 8, 9 points between exams, so it's more evenly spread out. So, all right, what would we expect? Where do we expect there to be the largest mean? We'd expect there to be the largest mean in exam 1, because in exam 1, we see that, we've got these exam scores clustered together around the AA minus range. So even though we have that, we do have this outlier that it's affecting it. So it might be pulling down the mean to something a little bit less than that AA minus range. However, we'd still expect it to be fairly high, maybe like high 80s, maybe low 90s, pulled down by that outlier. What data set do we expect to have the smallest mean? Well, here, we've got outliers in exam 2, we have outliers in either end, but the mean, it seems to be clustered in here. We might have a mean around 60 or so. And in this case, we have, for exam 3, we have a really even distribution between 12 and 96. We might expect the mean to be about the average of 96 and 12, so 96 plus 12 over 2. We might expect the mean to be about, 108 over 2. We might expect the mean to be about 54. So just, not with a full calculation, but with a little bit of looking in mental math, we might expect exam 3 to have the smallest mean. So we might expect exam 3 to have the smallest mean, but that's a little less clear-cut. So around 54 maybe. That's a little less clear-cut than the first question. For which data value do we expect to have the largest standard deviation, the smallest standard deviation? Well, when we look up at these 3 exams, again, we saw that exam 1 and exam 2 were relatively clustered together, even though they have outliers, whereas exam 3 is totally spread out. So we might expect the largest standard deviation to be exam 3. It is the most spread out. So they all have the same range. They all have a range of 84. So that's one way of saying that the spread is similar or the variation is similar. But we see that while the variation is the same between the two, while the range is the same between the two, these are all evenly spread out, whereas we've got groups clustered together. So exam 3 we see as the most spread out. What about the smallest standard deviation? Again, that's a little bit less clear, but my guess might be exam 2, just taking a quick look at it. It's either going to be exam 1 or exam 2. But these are clustered all closer to the mean of 60, whereas in exam 1, we sort of estimated a mean of around the high 80s. So both the upper cluster and the lowest value are going to be sort of farther apart from the mean. And so we think that maybe exam 2 will have the smallest standard deviation. Finally, for which data set will there be the largest difference between the mean and the median? Let's see. So differences between the mean and the median. We see that here there's an extreme outlier on the lower end. Here there's outliers upper and lower. So those two outliers might cancel each other out. Whereas with exam 3, there's really no outliers because everything's evenly spaced. Exam 1 might have the largest difference because there is one outlier on the lower end Exam 2 has outliers on both sides, maybe evening it out. So possibly evening this out, the difference out. And so what would we expect? We'd expect that the mean in exam 1 is less than the median because of the small outlier. Okay, so we did some thinking about these 3 questions, and it got a little bit messy. So below is just a summary of everything that we said above. There's no new information other than what we talked about, but this just summarizes kind of our thought process above and gives answers. These are the kind of answers I might expect if I have a short answer kind of question. Not just if I ask you to explain, then I'd ask for both the just short answer as well as some kind of explanation of how you arrived at those answers. If you wish, for extra practice problems, you could also calculate the mean, median, standard deviation of those 3 examples of exam scores just for extra practice. In the next bit, we're going to look at the actual calculated values for each of those and just see if our intuition was correct. Okay, so here are the range, standard deviation, mean, and median for each of those examples. The range is super easy to calculate. It's 84 in each. Just the largest data value, 96, minus the smallest data value of 12 gives us a range of 84. The standard deviation is a little bit trickier. Again, you can use it as a practice problem if you wish. The mean and median don't take too long, so those are pretty quick to calculate. So we said that exam 1 had the largest mean, and it looks like that is correct. So this had the largest mean, so great, our intuition was correct there. And it also looks as though exam 3 had the smallest mean, so our intuition was correct there as well. What else did we look at? We looked at the difference between the mean and the median. So in, in this example, the difference between the mean and the median was, if we do it this way, a negative 6.4 essentially, 6.3-ish. If we look at the difference here, we have the mean minus the median being approximately about 3 or negative 3. And here, if we look at the mean and the median, we see that the mean minus the median is about 0.25, negative 0.25. So yes, this is the largest difference between the mean and the median. You see that this small outlier of 12 is really skewing the data, whereas here, both 96 and 12 are outliers. These are each outliers, and so it's balancing that out a little bit. Although down here we see that the standard deviation, the difference between the mean, the sample mean, and the sample median is very small, and that's because the data is very evenly spread out. Are basically no outliers, and so that's why this difference is so small. Finally, we said which one is going to have the smallest standard deviation, which one's going to have the largest standard deviation. And so let's see. Here we've got our largest standard deviation, largest standard deviation 26.3, and that is what we expected because all the data values are evenly spread out. There's not going to be any data value that's very close to a mean, and we also expected that this set would have the smallest standard deviation, so that checks as well with our intuition, because it appears that while there are outliers, most of the data is clustered around the center, and so it appears that most of the data values will be pretty close to the mean, whereas in exam 1, the data values are clustered together but kind of far apart from the actual mean of 86.08. The last topic I want to describe in this video is the range rule of thumb. So the range rule of thumb gives a very rough estimate of the standard deviation. We saw that the standard deviation is a little tricky to calculate, whereas the range rule of thumb, the range is very easy to calculate. It's just the maximum data value minus the minimum data value. So this is nice that it gives you a quick estimate of the standard deviation, and that is that the standard deviation is close to the range divided by 4. So this is a very rough estimate. It is not necessarily a great estimate, but it's quick. So it's a quick, rough estimate of the standard deviation. As we saw in the previous examples, all 3 of those sets of exams had the same standard deviation, the same range, but different standard deviations. So obviously, it's going to depend on the situation. If we take a look at these exam scores, the range was 84, and so this gives an estimate of 84 divided by 4 for the standard deviation. This gives us an estimate that S would be approximately 21. And now we see, given these examples, that none of these are exactly what the standard deviation is. This is pretty close, this is a little small, and this is smaller, and this is larger. But note that it's not a terrible estimate, and especially given that a lot of people have a pretty good feeling about like mean as a measure of center, like sort of guessing what an average or a mean might be for a set of data. A lot of people have less of an intuitive sense of the standard deviation, like how large a standard deviation, a measure of variation might be for a set of data. So this can be a useful, quick estimate. Now let's use the range rule of thumb to estimate the standard deviation of a population. So for example, what do you think the mean or average height is of women in the US? What do you think the standard deviation is? Most people have a pretty close guess of the mean height, but have a little more trouble guessing the standard deviation. So the mean height for adult women in the US is 63.7 inches, or 5 foot 3.7 inches. When I ask students in class, a lot of people guess something closer to 5'5" or 5'6". And a reason that that's a little bit high is that you might know more young people, or people sort of in the prime of their youth, if you think about people as they age, they tend to get a little bit shorter. So by the time someone's 60, they've shrunk a bit. So if you guessed 5'5" or 5'6", it might be based on sort of knowing a younger group of people. But the mean height, or the average height of adult women in the U.S. is pretty close to 5'4", or just under 5'4". Now, a lot of people, as I said, have more trouble just having an intuitive guess for the standard deviation. So let's use the range rule of thumb to try to estimate it. To do that, we need to estimate the range. We're not given it. We have to think of it ourselves. And we have to then take that range and divide by 4 as an estimate of the standard deviation. So the range rule of thumb is actually best if there are extreme outliers, if we leave those really extreme outliers out. But think about, the tallest or the largest kind of usual value and the smallest sort of usual value. So in order to get rid of some of those outliers, maybe let's say, how tall would you guess the tallest woman at MCLA is? How tall do you think the shortest woman is at MCLA is? So use that as your maximum value and your minimum value in order to estimate the range, and then you can use the range rule of thumb to estimate the standard deviation. So pause and give that a try, and we'll talk about it in just a moment. Okay, so you have your own estimates in mind, and hopefully you've already calculated an estimate of the standard deviation based on the range rule of thumb. My estimates, I'm going to say that I think the tallest woman I've seen walking around on campus maybe is 5'11", and I'm going to say that the shortest woman I've seen walking around on campus is also just under 5 feet, maybe 4'11". So that would translate to a difference of 12 inches. If I wanted to, I could translate that totally to inches, and so this would be 71 inches, and this would be 48 plus 11, 59 inches. And so that would tell us that the range in this example is the largest value, 71 inches, minus the smallest value, 59 inches, and that would give us a range of 12 inches. So now I can find an estimate for the standard deviation estimate, and of course these values for tallest and shortest are also just totally estimates, but my estimate is that the standard deviation might be approximately close to the range over 4. So range over 4, that's 12 inches divided by 4, and that would give me about 3 inches. So my estimate for the standard deviation is 3 inches. If you haven't already, you could also do that yourself, find it for your values. And the true standard deviation, or closest to true that we know as humans, deviation. The true standard deviation is a standard deviation of sigma equals 2.5 inches. So this isn't exact, but it's pretty close, and I'm guessing your estimate wasn't too far off either. It's better of an estimate than we probably would have had in the beginning when I just asked what you thought the standard deviation might be with no information. So this true standard deviation of heights of adult women in the U.S. is 2.5 inches. Note I use the Greek letter sigma and the Greek letter mu as the mean and standard deviation here because we assume that this is for a population. We're not talking about one specific sample of adult women, but an accepted value for this population over time. So even though not every single adult woman has been measured and put into some massive database, there's still enough values taken over time that we accept that we have what we consider the population mean of about 5'4", of 5'3.7" inches, and a population standard deviation of 2.5 inches.